Vai começar.
Fala galera, bem-vindo aí, vocês estão acompanhando. Hello everybody, because today we're going to have a broadcast between Sou Java and Jugi Montreal. I would like to invite my friend Henry from Jugi Montreal to introduce himself and talk about to the speakers, to the people.
Bonjour tout le monde. Hello everyone. I will juggle with languages today. So glad to be here. The first time we do a joint presentation like that in the Montreal Java user group, and we're really happy. We have an awesome speaker and a well-known persona of the IT environment. So it's nice to get started like that. What do I do? I can do my pitch for those in Montreal. So we're trying to do a different talk in remote while we're at home, let's say. But we'll still thank some of our sponsors that you might show on screen if I think Rowan does it. For those who followed, Rowan lives in Montreal, so that's why he's able now to do two things at the same time.
That's great.
So that's awesome. I was told to tell one thing. So for Montreal or anywhere in the world, we're organizing an Oktoberfest. I think it's next week.
Yeah, October 1st.
Okay, October 1st. So you can look. I think maybe we'll post the link later, but you can look.
Just send to me. I can ask Chris to help us to put in the screen. Okay.
Do I have to? Oh no. How do you share my screen? No. Okay, I'll stop the sharing because it's boring. These were only the sponsors. I don't have it here, but I'll give it to you right after.
Okay.
And if you want to participate, I've created some issue for my own project, so EasyMock and Genesis, but there will be others. So if you want to get your hand dirty in first open source code, it's a really good way to do it because you have team leads from projects that can help you get started. It's here. The link is there. And then I'll shut up because I think I've said enough. I enjoyed the presentation, and I'll back to you, Juan.
Okay. Do you have it?
Yeah, I have it, but I need to. Okay. Let me. I have too many windows. I'll put it in the chat here.
Oh, the link over here.
Yeah.
Okay. And guys, if you want to participate, I'm gonna broadcast the Oktoberfest for you. Well, right now we're going to invite Bruno from Sou Java and our friend Monica that she talks about the clean architecture, and we invite her to do some couple questions. And our guy, Uncle Bob, welcome, my friend. Well, how would you like to? The stage is all of yours. We're going to share your screen, and we're going to leave the stage right now. Hold on.
Okay. All right. Well, so the stage is mine.
Yep.
The stage is mine. Welcome, everybody. I hope you're holding on for this one. This is a talk that I've done many, many times in many different places over the past several years. It's a nice evening talk. There's not an awful lot of code on the screen. So if you're enjoying a beer or a glass of wine, you don't have to worry because you're not going to need all of your neurons to follow along with this talk. Talk is mostly about the history of software, and it tries to project forward into where we think software might be going. That's always dangerous, right? I mean, predictions are always difficult, especially about the future. I think it was Babe Ruth who said that, if I remember correctly. In any case, when I give this talk live, I usually go through a little exercise with the audience. I ask everybody to stand up. And yes, I know everybody hates it when the speaker says, okay, everybody stand up. But there was a good reason for this. And so I get everybody to stand up. And then I ask all of the people with Y chromosomes to sit down. And who remains standing is usually a very small smattering of women. And then I ask this question: how did this happen? Why are there so few women in this industry? Why is it that computer science, that IT, that computer programming is the industry that has almost the fewest women in it of all industries? It's a deep mystery to me. The numbers in the United States are almost tragic. It's on the order of 3% of all the programmers are women. Why? Why did this happen? Now, I'm not going to try to answer that question here. In fact, that's not the topic of this talk. I just wanted to pose the question to get you thinking about that problem, because it is an interesting problem, but that's not what we're talking about now. What we're talking about now is a little bit different. I want to go back in time. I want to discuss with you the ancient scribes. The scribes of old, the scribes in Egypt, the scribes in Israel, these people were the only people who knew how to read and write. Reading and writing was not something that was allowed. Most people weren't allowed to know the skill of reading and writing. And in fact, the scribes protected their profession by making sure that there were laws passed that normal people could not read and write. They had a skill that they did not want to share. It was a skill that had to do with the writing down of characters so that things could be recorded. And both words and numbers were recorded. The scribes were the historians, the lawyers, the policymakers, the bureaucrats, the accountants, anything having to do with the functioning of civilization. They were at the heart of. And they were able to do some wonderful things. For example, they were able to make sure that laws were passed that no scribe ever had to serve in the army, and that no scribe ever had to pay taxes. We're going to have to talk about that soon, because I think that would be a good thing for programmers, not to have to pay taxes. In any case, we are the modern day scribes. Oh, we don't pass laws that prevent people from being programmers. It's just kind of an obvious thing that most people don't know how to program. We have a kind of literacy. We understand how to read and write code. Most people do not. And although we share this knowledge with as many people as we can, it's just not that many people, is it? And again, I'll bring up the topic of women. We probably ought to be sharing it with a lot more women and try to figure out a way to do that. In any case, we are the modern day scribes. Nothing happens in our society anymore without us. We're at the center of everything. It doesn't feel like that, does it? It doesn't feel like you're at the center of everything, but I will make that point as we go along in this talk. I will make the point that you and I are at the center of everything. But let's go back in time. Let's go way back in time. Let's go back all the way to 1936. In some ways, this was the beginning of our industry. You could go back further. You could talk about Charles Babbage. You could talk about Ada of Lovelace, the Countess of Lovelace, Lord Byron's daughter. You could talk about all of that. But I like to look at 1936 as the true start, because that's the first time there was real code. Alan Turing wrote this paper, and if you've never read this paper, it's a fascinating paper. And I recommend that you read it in the context of a wonderful book written by Charles Petzold, no less. And the name of the book is The Annotated Touring. It's a wonderful book. He takes Alan Turing's paper. He reproduces it in its entirety, but he chops it up into little tiny chunks, and then he surrounds each of those chunks with lots of history and discussion and explanation, so that by the time you've read this book, not only do you understand Turing's paper, you understand Turing, you understand the environment, you understand the history, you understand everything. It's a wonderful book. It is Charles Petzold's masterpiece. And by the way, I bring up Charles Petzold because many of you know that name. He's the guy who wrote all of the early MFC books from Microsoft, all that early library junk. He wrote all that stuff. And then to expiate his sins, he wrote a serious work, which was the Annotated Touring. In any case, I like to start back there at 1936, because in that paper that Alan Turing wrote, he presented code, real code that would execute on, it wasn't an electronic computer in those days, but it was a computer nonetheless. And in the act of creating this code, he also invented things like macros and subroutines. And if you read his paper, you will see this remarkable genius. And by the way, he wrote this paper to prove a kind of esoteric mathematical question that had been posed by David Hilbert years before. And that was all. He was just doing a mathematical proof. He invented our whole industry just in order to, prove this, obscure little thing called the decidability problem. But we don't need to go there. I don't want to go there. Now, what I want to do instead is talk about what happened to Turing after that, because you see his involvement in the concepts of computation got him involved in World War II and the code-breaking exercises of World War II. You know the story, right? The Enigma machine that the Germans had, and the Allies were desperately trying to decode it. And Alan Turing comes along and he finds a way by using computational hardware to break the code. And the kind of elements that were in the computers, and not really computers, but something like that Alan Turing was using, were these relays. They were electromechanical devices. Now, for those of you who don't know what a relay is, it looks like that. It's a coil of wire. And of course, if you pass a current through a coil of wire, it turns into a magnet. And if you look very closely at that picture of the relay, you'll see there's a little piece of metal that will be attracted to the magnet if the magnet is turned on. And that piece of metal will nudge some contacts, little switches, so that the switches will either, make contact or break contact. That's all a relay is. They were invented so that they could relay Morse code down telegraph lines. The signal would degrade after a few miles, so they'd hook up a relay at the end of the line, and the relay could refresh the signal as it passed on the line. It would relay the signal. Well, it turns out that you can compute with these things. You can do normal computation with relays. Now, they're not fast. They can do 10 cycles a second. but that's probably faster than a human. So they put together computational devices using these little relays. Now, you'd think they would have used vacuum tubes, right? Because they had vacuum tubes back then. The problem with vacuum tubes, however, is that they weren't really being mass produced, and they were unreliable. They were power hungry. They broke a lot. The filaments would burn out. And so it was very difficult to put together any kind of device with a lot of vacuum tubes in it that would maintain its integrity for any length of time. And so they were using relays until close to the end of the war. By the end of the war, they had started to use some vacuum tubes. I mean, the advantage to a vacuum tube is they're like 1,000,000 times faster than a relay. And they knew that. They understood that. They just, couldn't get them to work because they were unreliable. And by the time the war was over, they pretty much had the technology down, right? And they could have built the machine. In fact, they tried to build a few machines, but some of them actually did get built, and we didn't learn about that until later. But in any case, we moved on. And what did we move on to? Well, this is at the University of Manchester, and this is where Alan Turing moved, right? What you're looking at there is probably the very first entirely electronic computer. There had been some other machines built in Germany, a few years before. There was this guy named Zeus who had put, but we don't want to talk about them. We're going to talk about this machine, because this was an entirely electronic machine that Alan Turing wrote code for. And it was real code. He wrote programs on this machine. Now, we should talk about this machine because it's a really interesting machine. What did it use for memory? It had vacuum tubes in it. That's how it did its computation. But what did it use for memory? Well, the plan was to use these things, these Mercury delay lines. Now, what's a Mercury delay line? Well, a Mercury delay line is like a cylinder, right? Full of mercury, bigger than my cup, of course, a fairly large cylinder full of mercury. And what you'd do is you'd put a speaker on one side and a microphone on the other, and you would pump your bits into the speaker, and that would create sound waves in the mercury that would propagate through the mercury, and then there'd be a microphone at the other side that would listen for those bits and turn them back into electronic signals, which would be wrapped around to the speaker again. So this was like rotating memory, kind of like a disk, except it wasn't a disk, it was mercury. And the bits would rotate around inside these mercury delay lines. And Alan Turing was one of the designers of the machine, and what he had designed was a 22-bit machine, sorry for the fingers, 22-bit machine, right, with 1,024 words. 1,024 22-bit words. Now, that meant that he had to have 22 of these cylinders full of mercury, and they could hold 1,024 bits each. You can do the math on this, the speed of sound through mercury at room temperature and so forth, and you could get an idea of what the speed of the device was. But it was fast. It was hundreds of thousands of bits per second. So you could move, around that memory pretty doggone quick. The problem was they did build it, but the problem was that every time a truck would go by, it would shake the mercury and destroy the memory. So eventually they changed technology. Excuse me, and they changed technology to this cathode ray tubes. Now, some of you have seen a cathode ray tube in real life. If you ever had an old-fashioned television set, that had a cathode ray tube in it. The picture was on the cathode ray tube. And if it was a cathode ray tube, if when you turned off the TV, the picture would slowly collapse down into a little dot, and the little dot would stare at you for a minute or two at a time. And that was the old-fashioned TVs used to do that. Pardon me. Now, what a cathode ray tube is made of is an electron gun. There's an electron gun at the back. It shoots a spray of electrons forward, a tight little beam. And then there's little electrostatic plates that will let you move the beam back and forth, sweep the beam across the screen. And that's how you build up a picture. Turns out, however, that when the electrons hit the screen, not only do they make the phosphors on the screen glow, but they also deposit a charge. And the charge actually lasts for a little while. And the next time you sweep a beam across the screen, you can tell by the impedance of the current in that beam whether or not there's a charge on the screen. And so it's a kind of memory device. Now, what's interesting about this memory device is that you can read its contents on the screen. This was Alan Turing's output device. Alan Turing would record the results of his programs by storing them into memory cells, and then he would simply look at the screen and read the memory. This is how he got his first programs to work. Now, what kind of programs did he write? Well, he was interested in numerical stuff. And, back in those days, what could you do with a computer except, some number stuff? So he was interested in numerical analysis, but it was fairly elaborate numerical analysis. And he only had 1024 words, 22 bits in size. And of course, a computer can only have integers in it. So he had to invent floating point numbers. So he had to write like a floating point package. Have any of you ever written a floating point package? I mean, this is an interesting thing to do on a weekend. It's one of those kind of geeky things. You tell a family to go away. You're not going to be coming out of the basement for a good long time. And then you go down in the basement and you construct yourself a floating point package using only add instructions. No subtract instructions, no multiply instructions. Oh no, only add instructions, and you build yourself up a little floating point package. Do this one day. You'll gain a deep respect for the problem that Alan Turing had. But he had a bigger problem than that. What language do you think he was using? There weren't any assemblers. There weren't any compilers. He was using binary. Yes, that's right. He would code his code in raw binary. He invented a shorthand, which was base 32. You know, we like to use octal or hexadecimal. No, Alan Turing is base 32. And then he would enter his programs by punching paper tape with the right bits in it. Yeah, I'll leave you to imagine just how difficult that was. If any of you have ever written code in binary, I have, you know that it is no mean feat. In any case, Alan Turing wrote a bunch of code for about a year. And then he came up with this remarkable paper. This was actually a speech that he gave, and it was transcribed into a paper. And I'm going to show you excerpts from that speech. Here's one. Oh, sorry, no, it's this next thing. Good. He says, we shall need a great number of mathematicians of ability because there will probably be a good deal of this work to be done, this kind of work to be done. Now, how did he know? You know, this is the guy who was the first guy to write code to execute on an electronic computer. And by the time he had spent a year at it, he came to this conclusion. You know, we're going to need a lot more people who can do this. And what did he call the people who could do this? Mathematicians of ability. Are you a mathematician of ability? And then how did he know, you know, that there would be a great deal of this kind of work to be done? Now, honestly, I don't think he had any clue. I think if Alan Turing were alive today and looked around the industry, he would be just as startled as the rest of us are that there are so many programmers in the world and we cannot seem to satisfy our need for them. We want more and more and more of them all the time. But he still understood that the problem ahead, the workload ahead, was going to be enormous. And then he said something else that is even more prescient than that. He said this. One of our difficulties will be the maintenance of appropriate discipline. Okay, stop right there. You know where this is going, right? The maintenance of appropriate discipline. Because, he said, so that we do not lose track of what we are doing. Okay, now that's just the definition of every programmer in the world, right? How many of us maintain the appropriate discipline? How many of us do not lose track of what we were doing? So this is a remarkable observation from 5 years ago. Did I do that math right? I think I did. Roughly 75 years ago. This guy, after writing a bunch of code in binary, comes to the conclusion that we're going to need an army of people doing this, and they better be damn good at it. And the problem we're going to be having is maintaining enough discipline so that we don't lose track of what we're doing. It's a pretty good definition of our industry, I'd say. Okay, so that was like 1945, right? Now, how many programmers are there in the world in 1945? And the answer is 1. Well, okay, I mean, it was more than 1 pretty quickly, but there was this moment in time when there were no programmers ever. And then suddenly there was 1. And I like to think that that was Alan Turing. There's some debate about that. You know, might have been some other guy. But Alan Turing was certainly one of the first. And so I use the big O notation here. You know, the number of computers in the world is on the order of 1. It might have been coupled, but you know, probably 1. And the number of programmers in the world was also on the order of 1. Big O notation is very handy when you don't actually know what the number is. And you just kind of say, oh yeah, big O of 1. So, okay. Now this is 45 years ago, right? Did I do that math correctly? Let's see. We need 55 plus 20. Yeah, 75 years ago. 75 years ago. I think I got that right. 75 years ago, there was 1 program. Now that's 1 person's lifetime. You know, I'm 67, so I'm close to that. right? This is one person's lifetime. There are people alive today that were born before there was a computer, before there was a programmer. Just keep that in mind. All right, so now we're going to look forward a little bit. We're going to keep on moving forward in time. We're going to go from 1945 to the early 50s. And the problem of memory was a big deal, right? Because a CRT cannot hold a lot of bits, right? So, and they're expensive and everything like that. So eventually this problem was solved with this technology. This is core memory. Core memory, now that's made up of little rings. You see those little rings there? Those little rings are made up of powdered iron mixed with clay that is then fired and you know, in a kiln, right? The material is called ferrite. And those little rings are on the order of 1 millimeter in diameter. They're small. These are small little rings. And they are woven into a web of wires. And the purpose of this is to run current through those wires sufficient to magnetize the cores. Now, you notice how there's this kind of rectangular grid. So in order to magnetize a core, you need to surpass a certain amount of threshold current. If you pass less current than this through the core, it won't flip its magnetism. But if you pass slightly more than that through the core, it will flip its magnetism. So there's this threshold effect with the core. And the idea was that you would pass just over half the necessary current through the horizontal wire and just over half the necessary current through the vertical wire. And that would select a single core that would flip. And that's how you would record a bit in memory. If you wanted to read that bit, what you did is you flipped that bit to 0. You don't know what its original state was. It might have been 0, it might have been 1, but you force it to the 0 state. And then there's another little wire that snakes through every single core. And if a core flips, it induces a slightly delayed current into that wire. And a little sense amplifier can say, oh, I saw it. And you would know that the bit had flipped from 1 to 0. If you did not see that current, then you would know that the bit was already 0. Now the bit is 0 and you have to rewrite it. So the recording of memory and core memory required 2 steps. The zeroing of the memory and then the rewriting of the memory. Turns out, though, you can do that 1 million times a second. So, or more, not much more though, but about 1 million times a second. It depends on the size of the core. The smaller they make the core, the faster they can flip. So, you know, the focus of the technology at the time was to get those cores to be really, really, really small. Now, I had another problem. They're damned expensive to make. They have to be woven by hand. Oh, they had looms to help out, but there were people who had to sit there and, you know, thread those wires, little tiny wires through the cores and make sure that they were all aligned perfectly. It was very expensive to build. So memory like this in the 1950s would cost on the order of several dollars per bit. And, you know, in the 1950s, $1 was worth a lot of money. So, you know, to create a kilobyte was expensive. To create a megabyte was, well, at first it was just not even believable. It wasn't even approachable. Later on, it became approachable, but not right away. Something else happened in the 50s. Vacuum tubes got mass-produced in huge numbers. I mean, the radios and televisions, and everybody wanted all this electronics. And so these vacuum tubes started to get mass-produced. They became very low power, very reliable, very sustainable. And the idea that a computer, a significant computer, could be built out of these and marketed, and maybe more than one could be built, well, that became feasible. And so over time, computers were built. And IBM was one of the companies that would build these computers. Now, by the time 1953 rolls around, there are a bunch of computers around. And, you know, nobody wants to program them in binary. So, you know, somebody wrote an assembler, and then you realize, of course, well, you don't want to even write an assembler because that's horrible. And by 1953, John Bacchus has implemented the Spec for Fortran. This is a little bit of Fortran code on the screen there. And by the way, I also have a few other things on the screen. You see that punch card up there? Yeah. Okay, that's how I wrote my original programs back in the the very late 60s, the early 70s. When I was writing code, I would punch cards like that. And I wrote my code on that green piece of paper. See that down there? We wrote our code in pencil. You see, in those days, programmers did not know how to use a keyboard. Most programmers could not type. We used pencils, and we wrote our code on those coding forms down there. And then we handed the coding forms to people who would punch the cards. And then we would take the cards and we would hand them to the computer operators. Programmers were not allowed to touch the computer. You had to give your card deck to the operators, and the operators might, run them through the machine on a compile at 3 a.m. because, that machine was an expensive machine. It had to be kept busy 24 hours a day. So they wouldn't just stop the machine to run your compile. They'd make sure all the other jobs were done first. And then at 3 a.m, after all the jobs are done, they'd run your compile, which of course meant that you didn't see your compile until the next day. That was the way programmers worked in those days. You got one compile a day if you were lucky. Oh, I forgot a comma. Well, that's one day blown. So that was very common in those days. We had strategies to deal with that. But I just thought you ought to know. By the way, this is also the era that Lisp was born, right? McCarthy wrote Lisp in roughly 1958. And quite a few languages were built during this time. Fortran, Algol, Lisp, a few others. Very common. The machines they were running on were these machines. These are IBM 709s. And IBM made about 140 of these things. Right? They were expensive. They were multi-million-dollar machines. They required immense amounts of maintenance. You literally had to have a guy on site 24/7 just to keep the thing running, right? So it was very expensive. And the only people who bought them were research labs funded by the government, weather labs, weapons labs, things like that. Really, really rich companies might have one of these. But you needed a staff of programmers to run it. You needed a staff of maintenance people to keep it going. On the other hand, they were for the day, they weren't bad computers. They worked, most of the time they worked. They sort of didn't work all that well, but they sort of worked. Now, who was programming them? Who was programming these computers back then? Well, it was generally women. You knew I was going to come back to this one, right? Generally, it was women. Women were considered programmers in those days. Why? Well, because men built hardware, you see, and programming was considered clerical work. So they would recruit women to do the clerical work of programming. They didn't realize at the time just how hard writing programs actually was. So, of course, recruit the women to do the clerical work. This is a particular woman. Her name is Grace Hopper. She is the inventor of a language called COBOL. She actually didn't invent it, but she did kind of drive the definition of the language. And I'm not going to talk about COBOL for any length of time because it would be heartbreaking to do that. COBOL's a terrible language. Not her fault. The goal she set for this language was a wonderful goal to make programs readable by humans instead of these funny programmer type people. It didn't work out that well, and nobody knew back then that you couldn't do that well. Anyway, she was the eventually became the what we would call nowadays the CTO of Sperry Rand. It was one of the great computer programmers of her age. This is the person, Grace Hopper, who wrote the very first compiler and coined the word compiler. The reason we have the word compiler today is because she coined the word and wrote the very first compiler. There's another picture here I want to show you. These are all the programmers of the ENIAC computer at Princeton during the 50s. And you'll notice, of course, they're all women. And by the way, programming this computer was not a mean feat. Remember we talked about how hard it was to write programs in binary? Well, these people couldn't even write them in binary. They had to write them in wires. They had to wire the machine up, and that was a very difficult thing to do. Pulses would come at certain times, and they would plug those pulses into certain memory cells or certain arithmetic units, and oh boy, try and figure out, how the heck you're going to compute a problem by wiring it up. That's what these women did, right? So these were very respectable technologists, these women were. In any case, by 1960, the number of computers in the world was on the order of 100. I know it's hard to believe, isn't it, that there was a time when there were like, 100 computers. And, by 1960, maybe that number was 500 or 600. That's the value of the big O notation. You don't have to be precise about anything. But it was on that order, right? Something around 100. How many programmers were there? Well, roughly 10 times as many. On the order of 1,000. Probably like, 9,000 or 8,000, depending on, what month you pick. And why were there more programmers than computers? And the answer to that is, back in those days, there were no operating systems, there were no libraries, there were no frameworks. If you wrote, if the code executed, it was because you wrote it. Every instruction you wrote. That was it. You absolutely dominated these machines. And because these machines had to be kept running 24/7 because they were so damned expensive, you needed an army of programmers just to keep one machine running. So roughly about 10 times, 10 programmers per machine was a reasonable kind of ratio back in those days. But things were changing. I mean, who were these programmers? Who was programming these machines? We had to have thousands of them now. And the answer was, well, they weren't coming out of university, right? There weren't any university programs, there weren't any curricula. You couldn't get a degree in computer science. And there weren't any books written. There wasn't anything. I mean, if you were going to learn how to do this, you'd had to teach yourself. And so companies and laboratories would draw from their best employees, engineers, mathematicians, scientists, things like that. They would ask them, would you guys learn how to program this machine? And, these are the people who became the first programmers. And there's something about these people. First of all, a lot of them were women. That was early on. And then something else about them. They were all older. I mean, they weren't like 60, but they were all in their 30s or 40s or 50s. They were mature. They had been in the business for a while, and that's why the business chose them. The businesses would choose them because they trusted them and asked them, we trust you. Would you please touch this multi-million-dollar computer and not break it? So these are people who understood the business. They understood projects. They understood how things are done in business. And these are the people who became the first programmers. But the world was changing, and it was changing like crazy. The transistor had been invented, and the transistor could replace the vacuum tube. And all of a sudden, the machines could shrink, unbelievably shrink. They took much less power. They were much less expensive. Transistors can be mass produced at a rate much greater than vacuum tubes. And they don't take any power. Compared to a vacuum tube, they take a 10,000th of the power. Vacuum tube's got a filament in it. It takes a watt at least. These things were milliwatt devices, microwatt devices. So, people started thinking, whoa, we could build computers out of these things and they'd be really small and they wouldn't have a lot of power, wouldn't take a lot of power. And life changed very rapidly. By the mid-60s, IBM was using these little transistor devices to make thousands upon thousands of these machines, 1401s. They made 10,000 of them, and they were cheap. A company could rent a 1401 for $2,500 a month. Now, in 1965, $2,500 was a reasonable chunk of change, but it was in the reach of most mid to large companies. Small companies, maybe not, but mid to large companies. You could envision having one of these in your building, and you could have a staff of programmers, and you could do payroll on it, and you could do general ledger and bill of materials and inventory. You could do all this stuff on this. And so companies bought these things they didn't actually buy them. They rented them. Because IBM didn't sell anything in those days. They always leased computers, but people were doing it left and right. IBM made a decision in this time frame. They were going to be marketing to businesses, and businesses did math in decimal. So the 1401 was a decimal machine. Now, I don't want to mislead you. It still had bits in it, but all the bits were organized into groups of 4, and they encoded decimal digits, binary coded decimal, right? And the math that was done was all decimal math. The address arithmetic of the memory cells was all done in decimal. This machine shipped with 4,000 bytes of memory, not 4K, not 4096, 4000 in decimal. Anyway, tons of these machines were sold. By this time, the number of computers in the world was growing very rapidly. Now we're on the orders of tens of thousands of machines scattered around the world. And you know what number? Well, 50,000, 70,000, 80,000, something like that. The number of programmers in the world was still 10 times as large because, again, there were no frameworks, there were no libraries, there were no operating systems, hardly any operating systems. There were little tiny things. And so, you know, there were a ton of programmers just to keep these machines alive. Maybe on the order of several 100,000. This is 1960s, right? How many years has it been? It's been 20 years. 20 years since Alan Turing. 20 years, 2 decades. And now there's hundreds of thousands of programmers, tens of thousands of machines. Who are these programmers, these tens of thousands of programmers? Who the heck are these people, right? Now we're looking at 1965. I'm 13. I'm 13 years old. I've already written my first line of code, by the way. On a little plastic computer that my mother got me when I was 12. I might tell you that story later. There weren't enough engineers and scientists and mathematicians. There weren't enough trusted employees at companies, right? So the companies had to look around under their employees to find other people. And this is the era of the aptitude test. Companies started writing these horrible tests to see if you had the aptitude to be a programmer. And they would hand them to all their employees, and people would try and do these tests, and then they'd evaluate the tests. And, well, this person looks like they can, but that person looks like they can't. It was not a good time. The aptitude tests were not particularly good, but they did gather more and more programmers from the business, from their ranks of employees. And they were generally the smarter people and the better people. You know, it's just the way it is. And they would be drawn from the best and brightest of accountants and planners and marketing people and so on. And I like to think that Alan Turing would have looked at that under the definition of, you know, mathematicians of ability and kind of nodded his head and say, well, yeah, okay, because these guys, you know, they're still older. You know, they're in their 30s, they're in their 40s, they've been around the business, they understand the business, you know, they're mathematically sound, at least, they can probably write this code. So I'd like to think that although they weren't mathematicians, you know, they were experienced, disciplined professionals, and Turing would likely have approved. But things were changing really fast. By now, IBM was producing 1,000 IBM 360s every month. These were beautiful machines. I worked on several of these. I worked at a company once that had 2 IBM 360s just sitting on the floor. One of them had 64K of core. The other one had 16K of core, but that was an enormous amount of memory. 64K, my God, that was expensive. And these machines had lights. Oh my God, did they have lights? Look at that front panel. It's got lights. And when the machine executes, those lights all blink like crazy, just like in a science fiction movie. I think these science fiction people saw one of these and then said, yeah, we have to put that in our movie. These lights would blink because they represented all the registers in the machine. A good programmer could look at the pattern of lights blinking and debug their code. I did that a number of times. Why are the lights blinking like that? They shouldn't be blinking like that. They should be blinking in a different way. It was a wonderful time to be a programmer. These big, powerful machines, yeah, by today's standards, are minuscule little things. But okay, I mean, that was a great time to be a programmer. It was also a great time for the software industry because this is the era where almost everything happened, right? Ole Johan Dahl and Christian Nygaard in 1966 invent OO. They just invented object orientation. One day, you know, fiddling around with the language Algol 60, and they decided to, within the compiler, they were fiddling around with language features, and they moved the data structure from the stack to the heap. And oh my goodness, that's interesting. Now look at that thing on the heap. It's persistent. It stays around. Well, my goodness, we could put fields in that. We could put functions in that, and objects were born. It was a very remarkable time. It was also the time that Dijkstra came along, and Dijkstra said, you know, GoTo might not be such a good idea. He wrote the paper, you know, GoTo considered harmful. It was actually a letter to an editor, and it was the editor who gave it that title. But it was still Dijkstra's intent to communicate that, programming with GoTo is probably not a good idea. I'm not going to go through the rationale behind that today. It's fairly technical. I will say, however, that prior to this, GoTo was how we did everything. If you would have looked at the code that was being written in those days, every third statement was a go-to of some kind. If you had an if statement, you would go to different places. If you had a loop, you would go to different places. If you wanted to break out of the loop, you would go to different places. Go-to was the way. And here's this guy, he comes along, he says, yeah, probably not a good idea. He set the world on fire is what he did. The revolution that occurred because he said that was enormous. Now, in those days, of course, there wasn't any Facebook, so you couldn't flame anybody. But you could write letters to the editors, and I tell you what, the trade journals erupted in flames over Dijkstra's idea that you shouldn't use GoTo. But he eventually won that war. I won't talk about that more because we got to talk about these guys. This is 1968. This is Ken Thompson and Dennis Ritchie, and they steal time on a PDP-7 a few floors above them because their project got canceled and they didn't know what to do with themselves. And in that period of time, they wrote two rather incredible things, C and Unix. And they changed the world, right? They just changed the world. That's 1968. Look at all the stuff that's going on in this. This is a really fertile decade. This decade beginning in about 1957 with Lisp and ending in 1968 with C and Unix with objects coming right in the middle of it. Fascinating. One of the most fertile periods in the history of our industry. You'd like to think that, lots of really cool stuff happened in the 90s. Nothing like this stuff, guys. Nothing like this stuff. These guys in the 60s set the tone for everything. But the world was changing. Oh boy, was it changing. Digital Equipment Corporation had been born, and they were not using transistors anymore. Oh, they tried to use transistors, but then integrated circuits came along. Integrated circuits where you could put hundreds of transistors on a chip. I know now it's millions, but back in those days, it was hundreds, maybe dozens. And that was good enough because you could make these little tiny computers that can sit on a table. And how much did they cost? They cost maybe $100,000. Back in those days, they would have cost about $15,000. But in today's money, that would be like 120 or 130. Because, back in those days, 15,000 was a lot of money. So these things were cheap. Cheap. You could buy them. You didn't even have to lease them. You could just buy them outright. And companies bought them. Oh, by golly, did they buy them. There were at least 50,000 PDP-8s created. And that's just the PDP-8s. That doesn't count the PDP-1s, and the PDP-7s, and the PDP-10s, and the PDP-11s. These things were just hot off the market. They were just rolling off the presses. There were just tens and tens and tens of thousands of them. And Digital Equipment wasn't the only company making these things. Like, there were probably a dozen companies making little tiny computers. They were called, in those days, mini computers. That's what they were called, mini computers, you see. Because the word mini was that thing in the 60s, the level of ladies' skirts. They had started to make mini skirts. Mini, that was the word in those days, yeah. So these were mini computers. Now, by now, how many computers are in the world? Well, hundreds of thousands, probably in close to the millions, right? We're talking about 1970 here. We're now 25 years after Alan Turing wrote the first code in that computer at Manchester, right? And there are it's 1 million computers in the world, maybe 800,000 computers, 900,000 computers, something approaching 1 million. But an enormous number of computers, and more and more and more all the time. And the number of programmers was still on the order of 10 more, although by now it was starting to reduce because there were operating systems now. And there were not frameworks, but there were kind of libraries. The operating systems would ship with some library stuff in them. So there was some leverage, not much. Even in these times, 1970s. I would work on mini computers, and absolutely every instruction executed in that mini computer would be an instruction that I or one of my team members wrote. Right there. There's not a lot of code that we inherited from anywhere else, right? Even in those days. So there we are. We've gone from 1945 to 1970. That's 25 years. And look what happened in that period of time. It's an immense amount of progress. And by the way, it pales to the amount of progress that was made in the hardware after that. Moore's Law had just begun. Hundreds of thousands of computers, millions of programmers. Who were these programmers? Who were the programmers who were programming these machines in the early 70s? Well, here's one of them. That's me. I'm 18. And yep, I was a programmer. I did not go to college, by the way. I skipped college. I had learned to program in high school. I taught myself. My father got me books on COBOL and assembly language and PL1, and I absolutely inhaled those books. I could not execute any of my programs because the machines were too expensive, but I wrote the programs anyway. I taught myself how to program and became a programmer at the age of 18 and managed to get myself a job, and that's just the way life has been ever since. And, you know, that was me when I was 18 years old. And I was not alone. Although most the young programmers got through college. Because you see, there were tens of thousands of CS grads. The computer science curricula had been born. Universities were now training young people to be computer programmers. They didn't have a lot of computers in those days still at the universities, and they really didn't understand these mini computer things just yet. But they had enough computational hardware that they could start pumping out tens of thousands of grads, tens of thousands of young, incredibly young, very young programmers. And for some very strange reason, they were almost all men. Don't know why. Don't know why. You're still wondering about that right now. You know, how come the universities are pumping so many men out of degree programs and not as many women? And, you know, we still don't have the answer to that. Now, just to give you some idea, at my first job, there were about 24 programmers. This would have been like 1969, 1970, right? And most of these programmers were in their 30s or 40s. Like I said, they were older people. They had gotten recruited from some other part of the industry to be programmers. And roughly half of them were women. When I started it was a client service bureau in my hometown. They had 2 IBM 360s, and they brought me on board because they were just getting a mini computer, and they wanted some people to work on the mini computer. And when I went there, you know, about half the programmers were women. And that was no big deal. We didn't think anything of it. They were pretty good programmers too. One of them bailed me out of a nasty mess, I'll tell you. Anyway, these were older people of many of you know, men and women, roughly evenly split. But within about 10 years, I had changed employment by that time, and now I was working at a place that had about 50 programmers, and they were all really young. And they were in their 20s or early 30s, and only 3 were women. I mean, the change in demographics was enormous and very rapid. It took place over a period of about 10 years. And it's still like a big puzzle. It's like, what the devil happened? Why was there this change? And the change can be seen in this graph here. You see the green arcs there? The green arcs are women in STEM fields. And this is actually women entering university for STEM fields, and that red one is computer science. And you can see what happened. Like in the late 70s or something, there were plenty of women who wanted to be computer programmers, and then all of a sudden that just turned around and fell on the floor. And it's not at all clear why. I know there's lots of theories out there about why, but you know, none of those theories make a lot of sense to me. And I was there, and I still don't know what the heck happened. Maybe there's some women out there that might want to write about what the heck happened. Although, you know, I've seen a ton of theories. None of them make any sense to me. In any case, businesses had to have programmers. And what very young men lack in discipline, they make up for it in energy. And better than that, they're cheap. Oh boy, I'll tell you, my first salary as a computer programmer was $6,800 a year. I thought that was infinite, man. That would cover my car payment, and I could even give my parents a few $100s a month for rent. You know, that was just great. Of course, it was pittance. It was ridiculous. It was a stupidly small salary. But coming out of university, being a programmer, you could earn, you know, $8,000, $9,000 a year. I was earning $6,800 just before that period. I remember I remember dreaming of the day when I would earn $10,000 a year. Oh God, I could hardly wait. Now remember, up to now, the programmers had been disciplined professionals, right? They hadn't gone to school to learn to be programmers. They had taught themselves, by doing it. And they had been working in industry before that. They didn't need a lot of management or process because they understood business already, right? They knew how to manage their time. They knew how to communicate. They knew how to work together. They understood the way companies work. They understood projects. They understood deadlines and commitments and what to leave in and what to leave out. You know, the old Bob Seger song, right? They knew all that stuff. And so they didn't need a lot of supervision. But those people had worked miracles. Those people had done the IBM 360 virtual memory operating system. These were the people that put us on the moon, right? These were writing all the software at NASA. They had invented structured programming, functional programming, object-oriented programming. They invented the language, Fortran, COBOL, ALGOL, Lisp, C, Unix. They had done all of that. These people knew how to get stuff done. They were the original programmers, the early cohort, the older ones. And what process did they use? Well, if you had watched them, you would say, hey, they're doing Agile, because that's what programmers who, in the wild tend to use. Something short and iterative with lots of feedback. For example, the programmers on the Mercury space capsule, right? They did the avionics software for the Mercury space capsule. They wrote their unit tests in the morning and they made them pass in the afternoon. They were doing test-driven development. They were doing, short iterations. They were doing all this stuff. They didn't call it Agile. They didn't even know there was such a thing as Agile. But had you been there to observe them, you would have noticed, oh, they're doing something like Agile, aren't they? But hordes of young testosterone-driven boys were thrown into the industry, and they needed some discipline imposed upon them. They were not the consummate, mature employees that had begun as programmers. No. These are the kids who used to goof off at school, and then they'd write their senior program in the last 24 hours, and they'd pull all-nighters to do it, right? That's who was coming out of university, right? And managers looked at that and said, oh my God, what are we going to do with these kids? They need some kind of process. They need something to keep them disciplined and organized. And fortunately, or unfortunately, as the case may be, there was a process waiting for them, because a fellow by the name of Winston Royce had written a paper, and the paper he wrote had this picture in it. And it looked like water falling down rocks. And so it's called the waterfall process, right? And by the way, he wrote that paper to try and convince people not to use this as a process, because the whole point of the paper was that this didn't work. But nobody seemed to read the paper. They just saw the picture in the paper and they started doing this. And that reigned for 30 years. Now we're in the 1970s, and this is the era of waterfall. And in that era, by golly, for 30 years, we tried to make this work. And some of you remember, probably, trying to make waterfall work because it made so much sense. Oh my God, waterfall's got to work. There's got to be some way. It's got to work, but it never worked. Never worked. It always failed. And I don't mean to say that it always failed. It just failed a lot. It's a terrible idea. We didn't know. Now, at this point, I want to stop a little bit and describe our problem. We started in 1945 with one programmer. How many programmers are there in the world today? Now, I don't know. I don't know what the number is. It's some very large number. It's probably, on the order of 100 million. Might be more than that. Might be 200 or 300. I guess it depends on whether you count the VBA programmers. But one way or the other, it's on that order. It's like, big O notation of 100 million. Now, how do you get from 1 to 100 million in 75 years? Well, it's not linear growth, is it? Now it's probably exponential growth. And here we are, we're programmers. And, you know, if we're going to do exponential growth, we might as well use a base of 2 because we're programmers. So we'll use 2. And so what's the exponent of 2 that is close to 100 million? Okay, well, it's easy to calculate, isn't it? I mean, 2 to the 10th is about 1,000. So 2 to the 20th is about 1 million. And 2 to the 7th is, 128. So 2 to the 27th. 2 to the 27th is somewhere around 100 million. And that means that from 1945 to now, there have been 27 doublings. 27 doublings in the number of programmers in the world. And that's how you get to 100 million programmers. Well, okay, now that's over 75 years. So take 75 and divide it by 25, and what do you get? You get about 3. Do the number of programmers in the world double every 3 years? Well, actually, no, because in the first decade, it doubled much faster than that. I mean, Alan Turing may have been the first programmer, but a week later, there were 20. Right? And a month later, there were 100. So it doubled pretty fast in that first decade. Then it kind of slowed down. And there is very good evidence now that the doubling rate is on the order of 5 years. Every 5 years, the number of programmers in the world doubles. Now, that means that half the programmers in the world have less than 5 years experience. And this will always be true as long as we're doubling at a rate of once every 5 years. Half the programmers in the world have less than 5 years experience, which leaves our industry in a state of perpetual inexperience. There are not enough old guys around to teach the young guys. So the young guys have to learn it all over again. Every time, every new kid out of school's got to learn it all by themselves again and again and repeat the same mistakes and do everything wrong the same way over and over because there are not enough old guys around to teach the new guys what to do. There aren't enough mentors. You look around at a programming staff at a regular company, and what you see is a bunch of 20-year-olds, and you come to the conclusion that this programming thing, that's for young people. It's not for old people. All the old people leave it before they get old. No, we didn't leave it. We're all still here. It's just that there weren't very many of us back then. Now that leaves us with a problem. And what is the problem? Well, let me tell you what the problem is. Not that. That's not the problem. Although that's a good problem, but it's not the problem. The problem is this one. We are headed for a disaster. Why? Well, we're almost done. Only a few more minutes to go. I want you to look at your body at the moment and count the number of computers that are within a foot of your body right now. Now, I've got my phone. Okay, my phone. And how many computers are in here? Well, there's the display. That's probably got a computer. And there's the cellular radio. And there's the GPS unit. And there's the main processor. And there's the audio processor. There's probably about 5, 7, 12. I don't know. A lot of computers in here. But the one that really gets me, the one that I think is really interesting is this one here. See, there's a computer in the case. Because it's got a battery in it, right? And it communicates with the phone and tells the phone what the charge is. And there's a computer in the case, right? So I think that's pretty interesting, computer in the case. But that's not the only computer in the case that I've got within a foot of me, because you see, I've got my AirPods here, and my AirPods, yeah, they've got little computers in them, don't they? Doing Bluetooth protocol and stuff like that. And I don't know, how many computers are in each of these little things. There must be 1 or maybe 2. I don't know. I don't know what language they're written in either. But then, of course, the case has a computer in it. The cases have computers in it. Now, I've got a car key on me here somewhere. Oh, yeah, I've got a car key. I'm not going to show it to you, but it's got a computer in it. And gosh, oh, yeah, there's my watch. There's a computer in my watch. Oh, yes, there is. So the number of computers just within, on my body, just on my body at the moment is probably 2 dozen or 3 dozen. Look around at the walls, right? How many computers are on the wall? right? And if you were to look around my room, you'd see that thing on the back wall. That's a thermostat. Well, yeah, that's got a computer in it. And then there's the clock on the wall. Yeah, that's got a computer in it because it's, it's got a crystal and it counts the crystal. There's the TV set over there. You can't see it, but it's over there. It's got a lot of computers in that one. There's a little Roku device attaches to the internet. And oh, by the way, there's the hub over there. There's a couple of other computers over there. And you go upstairs, you'll find there's a lot of computers up there too, because there's a telephone up there. Oh, that's got a computer. And a microwave oven's got a computer. And the refrigerator's got a computer. And then you go out into the garage, and of course, all the cars have got dozens of computers in them. And here's the point here. There is nothing that you can do in a modern society without a computer being set smack right in the middle of it. You can't do it. You can't microwave a hot dog. You can't make a phone call. You can't drive to the store. You can't watch a television show. You can't buy anything. You can't sell anything. No law can be passed. No law can be enforced. No insurance premium can be paid. No insurance claim can be filed without a computer sitting smack in the middle of it. And that's just one computer. I mean, the whole internet, this network of massive numbers of computers everywhere. We are interacting with a software system virtually every minute of every day. Your grandmother is interacting with software systems every minute of every day. We rule the world. We programmers, we're the scribes. We rule the world. Other people think they rule the world. Then they hand those rules to us. And we write the rules that execute on the machines, that govern everything. And half of us have less than 5 years experience. So that's the disaster we're headed for, guys. It should be kind of obvious that one day, probably pretty soon, some poor programmer is going to do some dumb thing and kill 10,000 people at a shot. Just, and it wouldn't be hard to imagine what that would take, right? You'll think of the 737 MAX, for example. Or think of the Volkswagen thing, right? The cheating of the EPA. That was interesting, wasn't it? And think about Night Capital, the programmers who just happened to forget one little thing, and they lost $450 million in 45 minutes. Never mind all of that. The big event will be when 10 or 15 or 20,000 people are killed because some poor programmer forgot a comma, right? And when that happens, and it will happen, when that happens, the politicians of the world will rise up in righteous indignation. And they will point their finger right at us. You'd like to think they'll point it at your boss, don't you? You think they're going to point at your boss, don't you? No, but you didn't watch the CEO of Volkswagen North America testify before Congress, did you? And the Volkswagen CEO said to Congress, Congress said, "Hey, sir, how could you have let this happen?" He said, "Well, it was just a couple of software developers who did it for whatever reason. It wasn't my fault. It was them. They did it." So that's what's going to happen here, right? They might go to your boss, but your boss is going to have that finger right down at you. And by the way, that's fair because it's our fingers on the keyboards. We're the ones writing that code. We're the ones who forgot the comma and killed 15,000 people at a shot. And so the politicians of the world will point their finger at us and they will ask us the question. And the question is, how could you have let this happen? And we'd better have an answer for them. Because if our answer is, my boss told me it had to be done on Tuesday, if that's our answer, then the politicians of the world will hang their head in disgust and they will walk away and they will begin to plan the laws that they will pass. They will pass laws that force us to use certain languages and certain platforms and certain processes and get certain signatures and read certain books and go to certain courses. And we will all end up working for the post office. This is an outcome I would like to avoid. And I'd like to avoid it the way the doctors avoided it. You see, the doctors had the same problem. Right? Anybody could hang out a shingle and say they were a doctor, right? And then, these people are killing people. And so the doctors said, well, that's not stable. We're going to have to fix this. And they created a bunch of rules. And they learned how to enforce those rules. And they created an oath. And they made people take that oath. And if you disobeyed the oath, you were ejected. And that worked. For some reason, that worked. And bit by bit, more and more doctors joined that organization and took the oath. And eventually the government came along and said, you know, guys, we need to regulate you. And the doctor said, well, here's our rules. You can turn these into laws. Just do that. Take our rules, turn them into laws. And government, being fundamentally lazy, said, yeah, thanks, we'll do that. That's what we need to do. We need to come up with the rules. We need to come up with a set of standards, a set of disciplines, a set of ethics that we as programmers bless and promise to do and somehow enforce. Now, I don't know how we're going to do that. I'm not here to describe the mechanism. I just want you to think about the fact that that's where we're going. The world depends on us far more than they understand right now. And when they come to an understanding of just how much they depend upon us, it's going to scare the bejesus out of them. And they're going to want to regulate us. All of us. All of us. You might think, oh no, I just write code that runs inside of microwave ovens. The instant that microwave oven hangs on the internet, you're going to be regulated, because every microwave oven that hangs on the internet can be recruited by some hacker and used to do denial of service attacks on people they don't like. So everybody is going to be regulated. And we should get there first. We should get there first with a set of ethics, a set of standards, an oath, and a set of disciplines. And with that, I think I'll close this talk, because I think I've made my point. Thank you all for bearing with me. I know I went just a little over time, but if there are any questions, I would be happy to entertain them now.
Hello, Uncle Bobby. I would like to invite Monica to do our first question for you. She has a couple of questions. Monica, come on.
Hey, hello.
Hello.
I'd like to thank you, Juan, for the opportunity to be here today. And I'd like to thank you, Uncle Bob, for starting the conversation by questioning why we have few women's programming today. It's a great question, and we need a more representative environment. And my question is, since you see the future of programming in this way, in your opinion, what would be the first steps toward the self-regulation? And also, how could we programmers change our daily lives to be more imposing?
So I'll answer that by going back to one of the very first slides. And that slide was Alan Turing saying, we will need to maintain the appropriate discipline. What are our disciplines? What disciplines do we as programmers adhere to? Now, I have one that I use, which is called test-driven development. I follow it. It's a kind of dogma for me, and it's a good discipline. Do all programmers follow that? No. Should they? My advice is that yes, all of us should, but not everybody does. One of the things we're going to have to do over the next probably decade is figure out what these disciplines are. Test-driven development might be one, pair programming might be another, refactoring might be another. There's a whole bunch of them out there. What are the disciplines that we adhere to? And what are the cases when we can sidestep them? Right? That's just the first step. The first step is understanding what our disciplines are. Then we're going to have to identify what our standards are. What will we do and what won't we do as programmers? Doctors start out by saying, first do no harm. Okay, well, all right, what if programmers said the same thing? First do no harm. What does harm mean? We have to decide that. That's an ethical and a standards question. And once we've answered these questions, which I imagine is going to take several years, then we can start the process of figuring out, okay, how do we enforce all this stuff? How do we make one organization or many organizations that embody this view of programming and recruit people into their membership and can enforce the standards, the ethics, and the disciplines?
And a nice point. And difficult one.
A difficult, absolutely.
It's going to take a long time. but we can try to start like a little bit every day. And also we have another question that's from Elder. He's asking, like, do you think that programmers will rule the world someday? You said during the presentation that we rule the world today, but I don't know, because like there are politicians, like sometimes we need to do what they tell us to do. So are we going to really run the world someday?
Well, I hope that we don't rule it politically. We already rule the world. We just don't know it. Yeah, we do write the rules that run everything. It's just that other people hand those rules to us. I hope that programmers don't become the political leaders. I think that would be the wrong approach. Will we exert more power? Well, I think that's entirely possible. Can you imagine what would happen if every programmer in the world went on strike on one day? You know, we just said, okay, June 30th, we're not writing any more code for anybody. And the world would grind to a halt. We could exert an immense amount of leverage if we were ever unified. Now, unifying us is probably not possible. And I'm not sure it'd be a good idea, but it's something interesting to think about, isn't it? You know, we could hold the world hostage pretty easily if we were unified.
Okay, thank you for your answer. It's good. It's a good one.
Well, now I'm kind of the evil genius, right?
Yeah, amazing. Would you like to invite Henry? Henry from Jug in Montreal. He has a couple questions for you as well.
Hi. And now we have more time to talk. Normally, yeah, I talk a little bit. I like to chit chat at the beginning of presentations. Okay, I have actually, editorial comment. Actually, and for everyone who thinks we don't, I actually do think we almost rule the world, even politically these days. Like we see a lot of, and for people reading about how Facebook publishes advertising and everything, so we're pretty close to that. I'm not sure if it's evil or harmless yet, but those things are frightening, and we need good, well-meaning developers to help us not doing too much harm, I think. But that was my editorial comment. Then I had some kind of off-topic questions because it's rare that I have you in front of me, so I'll ask them. And by the way, so for those, Robert Martin wrote Clean Code and Clean Architecture, 2 great books. I do love Clean Code, and he applies a lot of the things he's saying about like doing good and being serious about what you're doing as a programmer are in Clean Code. So please do read this book. Buy it, download it, preferably buy it.
Yeah, I'd say buy it. Yeah.
but seriously, it's an excellent book that everybody should read, and that I recommend to everyone. That said, these 2 books are getting slowly old. I don't know if there's new editions prepared for them, but my question will be, what do you think has changed since you wrote them? What's not appropriate anymore in there?
Nothing.
Interesting. So it all applies.
When I write things, I like to write about the things that don't change. I like to write about, what makes code clean, what makes architecture clean, what are the principles of design, and these things have not changed in 50 years. And will not change for the next 50 years. These are very stable ideas. There are folks who like to write about the things that do change, the next framework, the next language, the next whatever thing. But there are other things in our industry that are very stable. That's what I like to write about. So for example, what's the difference between the code written today and the code written in 1965? And the answer to that is almost nothing, because the code in 1965 was if statements, while loops, assignment statements. The code today is if statements, while loops, assignment statements. More of them, but still the same thing. The nature of code has not changed. It's gotten, we've got tools. We got great tools, and we have languages that give us lots of cool and nifty features, but it's still just sequence, selection, and iteration. I could take a programmer from 1968, put that programmer in a TARDIS, send them to the future, put them in front of my laptop, show them IntelliJ, show them Java, show them all this fascinating stuff, and they would need 24 hours to recover from the sheer shock of the power. But then they'd be able to write the code. The code's not any different, you know. And I could take you and I could transport you back to 1968 and show you how to edit code on paper tape at 10 characters per second. And you would need 24 hours to recover from the sheer disappointment. But you'd be able to write the code because the code is not any different. So I write about things that don't change. I never have written a second edition of any book. I don't ever intend to write a second edition of any book. I always want to write what the next book is. Don't want to go back and fix the old book.
Makes sense. Thank you. I was thinking then the old programmer will look at Node.js code and all the libraries going around. He will say, "Hey, what the heck is happening now?"
Thanks God, I don't need to buy another version of my books. This forever.
And the other one is that's more. So I've seen a lot of your videos. Okay. Yep. You disappeared for a moment. A lot of your videos, and especially about TDD and mocking. I'm the lead developers for EasyMock, the EasyMock framework. So, and I know you're not a fan of mocking frameworks. You prefer to do them manually. And what I've seen these days is when we look at new languages like Kotlin, we see that in Java as well. We have records now, seal classes. There's a lot of things that cannot be mocked manually. And this, even if I'm doing mocking frameworks, this annoys me. But I don't see, like, it's a trend, so I don't see how we can get out of there. Do you think the languages are going the wrong way, or we just decide that mocking frameworks are now like a necessity and we do with that?
Are the languages going the wrong way? I think they are. The pendulum has swung many times, and right now the pendulum is swinging back towards very strong static typing, compile time checking. The pendulum had swung the other way in the early 2000s. It had gone in the Ruby and Python direction, dynamic typing. It had swung before that back in the 90s towards C++ and towards static typing, and it had swung in the 70s towards C, which was untyped. So this is a pendulum that keeps on swinging back and forth. And I think it's gone the wrong direction. I look at languages like Kotlin and Swift, and I think it's the wrong direction. Not only is it the wrong direction, it's an unnecessary change because these languages don't really implement anything new. There's no new idea in these languages. It's just a rehash of older ideas that have kind of been chopped up and sorted and stuck into them. So in that sense, yeah, I think languages are going right now in the wrong direction. The language I like to use at the moment is Clojure. That's a Lisp derivative. It works on the JVM, which is okay. I don't mind working on the JVM, but it is this nice Lisp derivative that lets me write in a very simple, very elegant language that I prefer. And it's dynamically typed, and I prefer that as well. The more languages implement features, the more difficult it's going to be to test those features, the more difficult it's going to be to build the mocking frameworks or the mocks to do that. The more programmers invent weirdo language stuff, the more difficulty we're going to have in writing the appropriate tests and writing the appropriate code for that matter. So my preference is for a very lightweight language, dynamically typed, that is very easy to read and write, and I'm going to use lots of tests to keep myself out of trouble. I don't need the compiler checking my types for me. I'm perfectly able to do that myself.
Thank you. I must say I'm not a fan of Clojure. I like my typing and I like my completion, but I was actually disappointed in the language. I don't like languages where you can do, like, there's many ways and like shorter and shorter and shorter ways to do the same thing. And I think they should have dropped that. I was perfect with Lisp. I love Lisp. So they should have stick with that, and I would have been happy. But that's my my personal opinion. But thank you very much for the answer.
Okay, I have a couple of questions over here for you. The first question is, which language do you think that evolved faster than others languages, and why?
Which language is
that get involved? Do you think that evolved faster?
Oh, which language has evolved faster?
Yeah. Like C#, Java, that difference in the orient object or functional program, something like that.
So I have a problem with the concept. I don't like languages that evolve. I like languages that come out and okay, maybe they go for a year or two, and they add a feature or two. Then I want the language to stabilize and stay the same. For example, I'm not a big fan of all those crazy question marks in Java generics. I think that's probably a very dumb idea. I don't like the fact that they're trying to cram lambdas into all these languages that were never designed for lambdas in the first place. I mean, and people, they're doing Java and oh, there's lambdas in here. That means we're doing functional programming. No, it does not mean you're doing functional programming. It's just another interesting way for you to have a pointer to a function. That's all. So that kind of stuff bothers me. Languages evolve until they become useless. This is what happened to C++. C++ evolved to the point where everybody kind of went, not doing it anymore. Java's close to that. C# is close to that. And that's one of the reasons that we keep on getting new languages, is that people keep on looking at these older languages that evolve so horribly that everybody goes, oh, God, no, and I need a new language. So I would prefer that the standards committees, after a couple of years, just lock the language and say, that's enough. Don't need any more. Now, one language that did do that was C. Right? They did a few little things to C in the 90s. They added a couple of little things. But after that, it just kind of sat there. Nice little language, works perfectly. Right? Nobody wants to use it anymore because it's a little bit primitive. But one of the reasons that C was able to be as long-lived as it was because the standards communities did not ruin it.
I have Branas helping me, Rodrigo Branas, that you did a live a couple of days ago. He sent me some questions, and there is no doubt that the C language is the most influential in the last decades. Why didn't Objective-C have success like C or C++?
Objective-C was a terrible language. So we have to go back in time here. This is a language that was invented in 1980 by a guy whose name was Brad Cox. And Brad Cox was a Smalltalk programmer. And he got hoodwinked into writing C, and he didn't want to write C. So he wrote a little preprocessor in front of C that he called Objective-C. And it made C look a little bit like Smalltalk. And he was so pleased with himself that he founded his own company called Stepstone. And he marketed Objective-C, and he marketed a bunch of libraries that he called ICPACs because he thought he was making software integrated circuits. And for a while, he was very successful. There were a lot of companies using Objective-C. This would have been about 1984, 1985. A lot of people using a few people were using Objective-C. And we're finding it pretty nice because it was a little better than C. And then along comes Jarno Strostrup, and Jarno Strostrup writes this wonderful book called the C++ Programming Language. And every C programmer in the world looks at that book and goes, oh, this is the next C. And they abandon Objective-C and they go full bore into C++. And Objective-C died that day. And it went into the garbage can and should have stayed there. except for a very weird accident of history, which was the board at Apple fired Steve Jobs. And Steve Jobs, with several $1 billion in his pocket, is out on the streets. And he says, well, okay, I'm going to go do the next thing. And he forms a company called Next, and he builds a computer called Next. And now he needs the Next software. And he sees a bunch of programmers out on the street, and they're holding up signs. We will code Objective-C for food. So he gets all these Objective-C programmers in and starts building the Next Step operating system, which of course is a dismal failure. Nobody wants the Next machine, except one guy, Tim Berners-Lee, who invents the World Wide Web on a Next machine, but never mind that. After a few years, the board at Apple goes, my God, we need Steve back. And they call Steve, and Steve says, yeah, I'm happy to come back, but I'm bringing all my guys with me. And he brought all his guys with him. And the whole Next project died, but all these guys came with him, and they started working on iPods, and they were all Objective-C programmers. Steve Jobs literally took this language out of the wastebasket and gave it new life, and never should have. There's no good reason for it. And then, of course, it suffered at Apple for a good long time, and people were writing iPhone apps, and they made extensions to Objective-C, and it evolved into a state that was horrific. And then somebody said, we need a new language. Let's make Swift. Why didn't they use Java? There are perfectly good languages. I know why they didn't use Java. They want to lock all the programmers into their own language. But, from a technical point of view, there are perfectly good languages out there. They didn't have to invent another one, for goodness sake.
Well, I have another question over here. And Brandon send me another one. Brandon's over here. I'm gonna invite him.
Hey, Bob.
There you go.
How's it going?
Pretty good.
Good.
Brandon, Rodrigo, I'm going to ask his opinion. In your opinion, what is the biggest evolution we had in terms of programming language? Do you think it was when we stopped to do some code based in 32 bits to use assembly, or when we stopped using GoTo? Is that from Rodrigo?
Yeah.
So the biggest evolution in programming languages was the move from binary to assembly language, right? That had a profound impact, right? Because writing in binary is really, really hard. So if you look at the way languages have evolved, right? The guys writing in binary took forever to do anything. If you can write in assembly language, you can go 10, 20 times faster. So that was a huge evolutionary step. The next evolutionary step was from assembly language to Fortran, say, some higher level language. Now, that was not as big a step. That was a smaller step. It was a good step. We like working in high level languages, but it did not make the same level of change. A person writing in assembly language probably goes 10 times slower than a person working in, say, Fortran. And then the next step would have been to a language like C. Now, from Fortran to C, maybe you get a factor of 2 improvement. You're going maybe twice as fast because you've got a lot of power in the C language, much more than Fortran had it. And then the next step might have been C++. Well, maybe you can go 20% faster in C++ than you can in C. Right? So, okay, that's a little improvement. And then the next change is Java, right? And maybe you can go 5% faster in Java than you can in C++. But you see where I'm going here, right? We're already way past the law of diminishing returns. Every new language, every new evolution of language adds the tiniest little bit of incremental productivity. All the early productivity was done in the 1950s. That's the stuff that really made a difference. The stuff we're doing now makes almost no difference at all.
Brandon, do you want to ask something?
Yeah. Bob, I was talking today to José Valim, which is the creator of the language Elixir.
Oh, yes.
Great guy. And I think that the things have changed a little bit after we starve with the Moore's law. and we started to grow our CPUs, the speed of the CPUs, and we start adding more cores, and like we need more functional programming languages which can bring us more advantages to our cores, our 2, 4, 8 cores that we are using in our computers, watches, cell phones. What do you think of this movement where we are using like the Erlang virtual machine with Elixir and Clojure and those kind of languages? What do you think about this kind of movement?
Well, I think that's a very natural kind of thing. The movement towards functional languages is driven by the fact that we need more and more cores, or more and more servers, or more and more processors. Moore's law is over. We're not going to get faster computers. That's ended. It's almost ended for density. So our computers are not going to get a lot smaller now. So we're at a plateau. Our technology is sitting on a plateau. And for the next N decades, we're going to be working at a level of computer power, which is pretty much the same as what we've got right now. And in order to get bigger things done, we're going to have to use more and more computers. Now that doesn't scale very well either. There's not a good way, at least modern, a way that we know of right now, to make use of 4096 cores. We don't know how to do that, and there's no chance that a processor chip is going to have 4096 cores on it either, because we don't have that kind of density. So we're not going to be facing that. What we are facing is a relatively moderate number of cores and servers. And in that environment, a functional language is very nice. Now, that's what Erlang was meant for. Erlang was meant for lots and lots of little tiny threads running in possibly multiple processors very, very safely. And Erlang is a functional language. And what makes it safe is that it's immutable. Variables are not mutable. There are no variables, right? So if you can't update a variable, you can't have concurrent update problems. So that makes it very, very pleasant to work in a multi-threaded environment. Elixir, I think, is cute. It's a kind of a Ruby dialect of Erlang. That's fine, fine. I don't mind it. I'm not convinced it was necessary, but okay. Erlang was a pretty good language too. Fine. Are we all going to be using Erlang? I don't know. My guess is no. But I do think that we'll be using something like Erlang. And again, I would go to a Lispy language instead of a syntaxy language like Erlang. But I would probably go towards a Lisp sort of syntax instead of that.
Yeah, great.
Well, we have some questions from the people over here. I selected the one. What are his thoughts about quantum computing and neuroform?
Okay, two very interesting topics, two very different topics. Quantum computing. I will get impressed with quantum computing when they can get a couple of qubits to stabilize for more than a millisecond. Right now, they can't do very much with quantum computing. There's a lot of potential, but even the potential is limited. These are not general purpose computers. Quantum computing is not a general purpose technology. There are certain things that you can do very fast. There are other things that are just as slow as a normal computer. So, for example, the traveling salesman problem, the vast combinatorial explosion of trying to figure out the tightest network for a traveling salesman. Quantum computer is not going to be able to do that any faster than any other. There are certain things that a quantum computer can do faster that have to do with parallel multiplications and things like that. So I am not looking forward to quantum computing revolutionizing the software industry. I think it'll have a place, especially in cryptography and stuff. But most regular old programmers are probably not going to pay much attention to it. Now, neuromorphic programming, machine learning, right? Artificial intelligence. This has gotten a lot of hype in recent years. I think that hype is entirely misplaced. I do not believe we will have sentient machines anytime in the near future. I do not believe that we will have self-driving cars in the near future. And by self-driving cars, I mean cars that we trust on the road in all weather conditions, in all neighborhoods. I do not believe that you will get your phone and you will dial up an Uber and have a driverless car pull into your driveway, and that you will get in and you will tell it to take you to Walmart, and it will take you to Walmart, and then you'll get out of it and it'll drive away. I do not believe that will happen. What we might have, and I think probably will have, are driverless trucks on highways, because that's a very constrained environment. It's very safe. I don't think they'll get off the exits, though. I think a human will get on at the exits. You might have some driverless cars on extremely safe city routes, but they're not going to go into residential neighborhoods. You're not going to have your 2-year-old walking into the street and a driverless car, and trust the algorithm of the driverless car. I was driving a Tesla, test driving a Tesla, and the salesman was sitting next to me. And the car has front-looking radar, and it's very cool, and it can see the road. And so I did a few experiments with it. I turned on the autopilot and took it down a normal road, and it did a very good job. Fine job. It'd turn the corners, would do just fine. Then I took it down a road where there was some construction and some barricades. It had no idea what to do. It would have plowed right into those barricades if I hadn't hit the brake. And then we're driving along, and going about 40 miles an hour, right? And we're coming up to a red light. It's about a quarter mile ahead. And there's cars stopped at that red light. And the salesman sitting next to me says, "Trust the car." And I looked at him like he was insane. I'm going to trust the car to stop? No, I'm going to put my foot on the brake and stop the damn car. I'm going to trust the car. I don't know what the programmer was doing when he wrote that code. I don't know if the programmer wrote any tests when he wrote that code. I have no idea what's going on inside that car. I'm not going to trust that. So that's my end result there. I don't think that the hype of machine learning is going to pay off. I think there's some very good things that you can do with machine learning, but I don't think the hype is going to pay off. I think it's been overhyped and oversold just the same way it was in the 80s and caused a real loss of funding for all the artificial intelligence researchers in the late 80s and into the 90s because of the oversell.
Okay, we have another question. Okay, this one. Without the agreed open coding standard, how are Navy young people who pick up programming supposed to meet Uncle Bob standards for future programs?
Well, I like the idea of standards, and I don't mind a coding standard. I think a coding standard is a good idea. A team of developers working together should have a standard by which they code. That standard should be in their code. I don't think they need a document. It should just be in their code, right? And if you read their code, you will see the standard by which they code. You will see what they follow. The reason people write coding standard documents is because their code does not follow the standard they want. And so they write a document that's trying to convince everybody, please stop doing it the way you were, and please start doing it this way. And my answer to that is no. If you want a coding standard, you make the code you're working on conform to that standard, and then that code will be the coding standard document.
Great. Well, I have just a last question. I'll bring everybody to say thanks. When is going to come the book, The Future of Programming?
I have several books that I'm working on right now. One of them is called Clean Craftsmanship. That's the working title anyway. I have one more book after that I know I'm going to write, which is going to be on the problem of professionalism and standards and disciplines and oaths and things like that. And then it's just possible, tickling me in the far future, that I might write a book about closure or something like that, but I'm not at all convinced of that last one.
What's your favorite language?
At the moment, it's closure.
Oh, got it.
I think it's a great language. I prefer writing in that than just about anything else.
Okay, I would like to invite Henry, everybody that's in this live to say thanks for the times of Uncle Bobby. Harry, it's from the Jugi
Oh,
Montreal,
I'm here.
Jag leader. Okay.
Yep.
Chris, Brana, Monica, Cameron, everybody over here. Okay. Say something, Henry, to say thanks for Uncle Bob and for Jugi Montreal people.
So yeah, two words in French. Merci à tous d'être venus pour cet événement. C'était bien agréable. And thanks to everyone to have been there. It was a great event. Full translation. Thank you, Mr. Martin, for attending. And it's been a pleasure. Hope we'll see you in person one day when we'll be able to.
Yeah, one day.
Yeah.
And hello to Brazil, which I've had the pleasure to visit twice, but I think I've never been there more than 48 hours for 2 conferences. So I need to be there for a longer time. But I have great food and great
Last time
friends
you go
this
with me. The next time you're going with me.
Perfect. I know. Ciao, everyone.
Well, Chris, do you want to say something?
Eu tô aqui só fazendo trabalho sujo e eu vou no português mesmo, galera. Galera que tá aí no Brasil aí, obrigado aí a todos. Uncle, thank you. Juan, fantástico. Conte sempre que o papo precisa de mim aí para ajudar nas transmissões do Sou Java, do Jogo Montreal. Eu tô quase aprendendo. E é isso aí, galera. É um prazer estar aí com vocês e eu tô aqui no backstage. Mônica?
Okay, Monica.
Em português?
Whatever.
Okay, so thank you guys for this amazing talk. Thank you, Mr. Martin, for all this information that you brought to us. And that's it. Thank you, Juan, too.
Okay. Bernas?
Well, thank you so much, Bob, again. We had the opportunity to talk last week. It was a great pleasure. Thank you, Juan, Monica. Merci, Henri, toutes les personnes à Montréal. Cristiano, obrigado também. Uncle Bob, thank you so much. Hope to see you again.
Pleasure.
My pleasure.
OK. Merci à toutes les personnes qui regardent du YouTube channel de Montréal. Thank you, everybody that watch from Montreal channel and Brazil, Sou Java channels as well. Okay, and thank you, Uncle Bob, for your time. That was an amazing presentation. I hope we can meet each other in person when the COVID stuff ends.
Yeah.
And I can have opportunity to watch your presentation or webinar in person. Okay. And that's it. Thank you, everybody. Thank you for all the participants. Thank you for the people that watch it. And I hope you enjoy a lot. Thank you. Bye.
Bye.
Have a good night.
Bye-bye.